We are now in 2.3, day 1. It's just a little slightly extra piece on 2.1. We're going to be talking about the vertical motion model, which is very similar to the one that we've looked at before. It's just going to add on a bit of a new piece, and that is this velocity piece that we'll be seeing here on part of the problem for the example. Now, these motion models are a little different maybe than what we saw earlier in the year, because they don't have this g substituted in. G is the acceleration due to gravity, and since we're on Earth, that is going to be measured in 32 feet per second squared. If we're using the metric system, we can use 9.8, but that's not what we'll do in these problems. If we plug in the 32 feet per second squared for g in each one of those, then our model becomes what you see down here. Remembering that t stands for time, v, that one's going to stand for initial velocity, or v sub 0, I should say. S sub 0 is initial height. And then if we go over here to the second equation, v sub 0 is also going to be initial velocity in this case. I should also mention here, s of t, that is a function that means height, and then v of t is velocity. So we're going to go with those two models, and they will both help us to solve a problem that we'll see next. It's a problem that comes from your book, but should be a good example for what you're going to be doing in your homework later on. So we've got, it says free fall motion is promotion for the Houston Astros baseball park. Competitions held so you can throw a baseball from the highest from the front row of upper deck seats, 83 feet above field level. The winner throws the ball with an initial vertical velocity of 92 feet per second, and it lands on the infield grass. Somehow they're able to measure that speed, so we'll assume that that's okay, and we're going to use that 92 and plug it into these formulas. So we've got the 92, that's the initial velocity, and then 83 is going to be the initial height above the field. So when we plug those in, just looking at these equations here, that's going to mean that s of t is going to be negative 16t squared plus 92t, and then plus 83 for the initial height. Then velocity, we're going to use that formula here at some point, so we might as well write the velocity formula too. V of t equals negative 32t plus 92. A couple of different formulas that we'll use throughout the process here, but you'll find out as we go along what that's going to be. So now we got to go down to these problems, and we got to see, all right, part A, find the maximum height of the baseball. That's going to be from our s of t formula. So what I'm going to do with that is I'm going to enter it into y equals, as you can see right here, and then graph it. Now if I'm in my standard zoom window, we're not going to see much on this graph. It looks like it's going really high up here, and so I need to adjust this window. I would adjust it by taking clues from this function here. So you see 83, that was the initial height that we went from. So we're going to go to y equals, or excuse me, we're going to go to window and change the y max to at least 83. I'm going to start with 100 because it's got to be more than that, I would think. And then see how far up it goes. Whoops, I may have changed the wrong one. Yes, I did. I changed the x max. That's not all right. Let's change the y max to 100. That looks a little bit better, but as you can see, we still need to go up a ways. So I'm just going to start doubling it and see when I have everything I need. Almost there. Maybe I don't have to double it this next time. I'll go to like 250 so that I can see the entire shape of that graph. So now, much easier to see what's going on here. So let's go back to our questions. So it says, find the maximum height of the baseball. I can do that using the calculator by going second trace, and then maximum. And so I can use this feature, go left boundary, right boundary, and a guess. And so it looks like my maximum height here is, we're looking at the y value, that's what makes the height, is so it's 215.25, and so it appears that that's going to be in feet, 215.25 feet. Okay, 1 down, 2 to go. Next is how much time is the ball in the air. Now the way that we know how much time it is in the air is until it hits the ground. So if you look over here and we just want to try to find out when it hits the ground, and that x value will tell us the number of seconds. Now we could go over here just to get an idea to start with. Looks like it's maybe somewhere around 6 to 7 seconds. But if I really want to get this, I can go back to second trace, go to 0, left boundary, hit enter, go back here, right boundary, go back a little towards it, and this 4e to the -1, that just means it's really, really close to 0, but it looks like here we've got about 6.5 seconds, so we'll just round it to 1 decimal place here, 6.5 seconds, because that is the x value that indicates the time in this case. Now we want to take a look at what is the this last one's a little different. It says determine its vertical velocity when it hits the ground. So kind of like the very second before it hits the ground, we want to know what the velocity is. Well, here's our formula for velocity. We just need to know when it hits the ground. We just found that with that 6.5 seconds. And so what we'll do is we will now just plug this 6.5 in. I think a little bit better estimation was 6.54, maybe just to be a little more accurate, I'll go with that. So now I'm going to plug in, this is part C, and so V of 6.54, because that's the time we're looking at, is -32 times 6.54 plus 92. So punch that in. And what we're looking at is about -117.28 feet per second. Now that is maybe a little bit different than what you see on the completed notes, because I think on the completed notes I use 6.5 as the estimate. But either way, we have something pretty similar here. -117 feet per second. Now it is okay to have a negative velocity because it's going downward. So even though that seems like not something we're used to seeing, it's okay when we're talking about velocity. Speed would be a different story, but this one is going to work out okay.